Okay, so in this case, we're trying to prove that this language is not a regular language. What would be a string, a good string that would break this? So the natural thing to try is something like AP, B, what? What should this be? If this is a P, no, this is not related. This is an M. Yeah, exactly. Q. Why Q? It has nothing to do with this. So this is an M. There is no relation between M and N. They are independent. So use a different symbol. And then this is another P because this is the same as this. And so this string belongs to the language, belongs to L. So this is L. Now, the pumping lemma, remember the conditions of the pumping lemma. Condition number 1 is x, y, I, z belongs to L for I greater than or equal to 0. Condition number 2 is the value of y should be greater than 0 or greater than or equal to 1. And condition number 3 is xy is going to be less than or equal to p. So the repeatable, translating this in English, the repeatable part must appear within p symbols. The repeatable piece must appear within p symbols, or within the first p symbols in the string. And what does this condition tell us? Yeah, y cannot be the empty string. It must contain at least one symbol. So here, in this case, where should the y be? Within the first p. So the y should be here, somewhere here. What does that mean?
If you pump it, you'll have more A's on the left than the last AP.
Okay, yeah, exactly. So if you pump it, you will have more A's, but you're missing pump it up or down. If you pump it up, you will get more A's. If you pump it down, you will get fewer A's. And pumping down means using I equals 0. That's what pumping down means, right? So this is this is your balloon. This is Y. So if you pump it up, then this is Y repeated twice. Pump it up, Y 3 times. And if you pump it down, then this is, you shrink the balloon. So this is Y0. Okay? So this is what the pumping lemma means. The whole idea is to show that there is a string that is large enough such that if you pump it, it will give you a string that does not belong to the language. So here, y must consist of only zeros, only A's. This means that for I greater than 1 or greater than or equal to 2, there will be what? More
before BQ than the A's after BQ.
Right, exactly. Yeah. So don't make the mistake that I made the other day. So it's not more A's than B's. It's more A's before the B than there are after the. So there will be more A's before BQ than there are after it. And for I equals 0, by the way, this is not necessary. If you show that pumping for one I will produce a string that does not belong to the language, this should be sufficient. It will be sufficient to show that one I, whether it's pumping up or pumping down, if one I is going to produce a string that does not belong to the language, then this is sufficient. For I equals 0, there will be fewer A's. And you write the rest. You write the same thing. Fewer A's before the BQ than there are after. Okay? Yes?
How do you decide where Y is?
We know for sure, well, xy less than or equal to p. So it should be within the first p character. So it's going to be somewhere here. We don't know where. Right? So this is 0. This is index 1. This is index p. And y is going to be, we know that it will be somewhere here. We don't know exactly where. But wherever it's going to be, we only have A's. That's the point. It can't have B's in it. Because from 1 to P, what do we have? We only have A's. Okay. All right. So next. So this is. So that was easy, in fact. The other one is NA of W equals NB of W. Equals NB of W. Now same number of A's and B's. Now I can use this AP BP. This has the same number of A's and B's. And clearly if I pump this, the Y must be here. So if I pump it, what will I get?
More A's.
So pumping up will give you more A's than B's. Pumping down will give you, less A's than B's, or fewer A's than B's. Okay? So this is straightforward. Next question is AN BM. Okay, looks like it's maybe a better. AN BM such that M is greater than or equal to 0 and N is greater than M. Okay. So now what should my string be? I need a string that belongs to this language where the A's are more than the B's. Yeah. Now what should the string be here? A string that if we pump it, we will get a string that does not belong to the language. So I'm giving you a hint here, pump it down. So pumping down means what?
Decrease.
I equals 0. So what is a string? If pumped down will give a string that does not belong to the language. So here AP, B, does that belong to the language? No, it doesn't.
P minus 1.
Yeah, you can do P minus 1 or you can do this P plus 1. Either way. So you should have at least more. So this is a string. You only need to come up with one string that if pumped gives you something that does not belong to the language. And this is something that now now here again, in fact, Y is going to be before the last A. So but it will consist of only A's. So Y, or because of condition 3, Y must consist of only A's. So if we pump this string down, we will get a string with, or a string, let's say, S prime, in which the number of A's What can you say about the number of A's in a string that comes from pumping down?
Equal to the number of B's, which doesn't say.
Equal.
Not necessarily equal. Why not necessarily equal?
Or less than.
Yeah, equal or less than. Because when you say equal, you're assuming that y consists of a single A. But y may consist of multiple A's. So it's going to be in which the number of A's is less than or equal number of B's. So this is what pumping down means here. Yes?
But if we chose the string a p plus 1, if we subtract 1, wouldn't it be p equals to p?
Yeah.
Still, it will not be. Yeah, so equal is not in the language. So the language, n is greater than m. So you should have more A's than B's. So the string AP, BP does not belong to L. Because P is not greater than P. Right? So the number of A's must be greater than the number of B's.
So can you pump down like to the negative numbers?
No, we're not pumping to the negative numbers. So, okay, so you have this string. So, A, B, B. Does this belong to the language?
Yes.
Yes, it does. It has more A's than B's. Suppose that this is Y. Pumping down, what does pumping down here mean?
Get rid of it?
You get A, B, B. Does this belong to the language? No, does not belong to the language. If you pump it up, what will you get?
More A's.
A, B, B. So pumping up will still give you strings that belong to the language. That's why pumping up will not help you prove that this language is non-regular, because it's indeed pumpable up. So if you pump it up, you will make it even better. You will still satisfy the condition of the language, which is A is greater than B.
And how is it possible to get less a's than the number of b's?
No. Less A's than the number of B's? Yes. So suppose that Y is this. So Y can be anything less than or equal to P. So if Y is this, what will pumping down give us? It will give us A, B, B. Do you see the pumping down? Pumping down is this repeated 0 times instead of repeated 1 time. Now pumping up in this case will give us what? Pump it up with, this is with I equals 0. With I equals 2, you will get what? A, B. So this is the pumping. So this is Y repeated twice. This is Y repeated once. This is no Y. Y repeated 0 times. Okay. So next. So next is, in fact, it's the same. I'm going through this one quickly because it's the same. A, B, N, A, M. And n is greater than or equal to 0. N is greater than m. And now here, let's try the string what? A, B, what? Let's try P plus 1, right? And A, P. Now, or you can do P and P minus 1. It's the same thing. You can do P and P minus 1. Maybe it will be easier to do P and P minus 1. Now in this case, I know that Y is going to be somewhere here. So what do I have here? I have AB, 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 lots of ABs. I know for sure that my Y is going to be somewhere here. Now, That's what this tells me. X, y is less than or equal to p. Now my y, will it consist of A's or B's or A's and B's? In fact, it's clear that if the y has only A's, if your y has only A's and you pump it, you will not get a string that belongs to the language. Why?
Because you know, it's having BB.
Yeah, it will not be A. So let's pump this. Let's pump this. Let's pump and look at this section. Let's look at this section after pumping. After pumping this section, you will get AB, AA, B. Does this belong to the language? No. So this section alone shows us that pumping an A only will not give a string that belongs to the language. So pumping only A's, so with y equals or y consisting of only A's, you will get a string that does not belong to the language. And same applies to a y that has only B's. In fact, the only reasonable y should have what? Yeah, same number of A's and B's. So it should be like a whole. It should have an even length with the same number of A's and B's. That's what would be a reasonable y. A y cannot be only A's or only B's, or it cannot have more A's than B's or more B's than A's. Okay, so now assuming that y is going to be AB plus, repeated one or more times. Now in that case, how can we show that this will give us a string that does not belong to the language? Again, pumping down. Yeah. If you pump it down, now you will have the number of ABs is going to be less than or equal to the number of. So if you pump this down, and I can't write everything now, so I'm going to write very briefly. If you pump this down, you will get a string S prime in which the number of ABs is less than or equal to the number of the A's that follow that. You know, the A's that follow, I mean by the A's that follow, I mean these A's. Okay? So these are, I think, we have done enough examples to, explain the pumping lemma. And now we'll move to the next question. There are some quick questions that we can go through easily, quickly. So this is a prove or disprove. Prove or disprove. Number one, if L1 is regular, then L2 that consists of all the strings in L1 that contain the substring X but do not contain the substring Y is regular. So is this regular? I'm not going to write it. So L2 that has all the strings that have X as a substring but do not have Y as a substring, is this going to be regular or not? Yeah, so why? So give me the idea.
Intersection and complement.
Okay, that's exactly the idea. So L3 is going to be the language of sigma star X sigma star. So this is the language that has the strings that have X as a substring. And L4 is going to be the language of sigma star Y sigma star. And then our L2 is equal to L1 intersected with intersected with L3 intersected with complement of L4. Complement of L4. And so you have to write this, and I'm not going to write it. So in order to answer, you'll have to write that this is regular because it's expressed by a regular expression. L4 is regular. And regular languages are closed under intersection and complementation. This is a key idea. Regular languages are closed under intersection and complementation. Okay, so this is true. Number two, if L is a regular language with an infinite number of strings, then L is not equal to LR, where LR is the reverse language. So then every language that consists of an infinite number of strings is not equal to its reverse language. Is that true or false? False. Then you should give a counter example. What's the counter example?
All the strings are
Palindromes. Yeah, exactly. Example L is W such that W is a palindrome. Okay, so how many people got this right? Okay, the majority. Number three, if L1 is a regular language and L1 intersected with L2 is not a regular language, then L2 is not a regular language. So L1 is regular and L1 intersected with L2 is not regular, then L2 is not regular. Is this true or false? Yeah, this is true. How do we prove it? How do we prove it? So it's the contrapositive of closure under intersection. So L1 is regular and L2 is regular implies that L1 intersected with L2 is regular. Now the contrapositive, what's the contrapositive? So the intersection is not regular. If L1, so it's the negation of this, implies the negation of this or the negation of this. Okay, so L1 intersected with L2 is not regular. This implies, so the negation of this and this is the negation of this or the negation of this. So you should go back to your logic, to the logic that I assume you have had in CC 28. So L1 is not regular or L2 is not regular, but it's given that L1 is regular. So we're given that L1 is regular, therefore, and L2 cannot be regular. But L1 is regular, therefore, L2 must be non-regular. So, intuitively, what this means is that if both languages are regular, then the intersection must be regular. And if we know that the intersection is not regular, then we know that at least one of them is non-regular. This is the the intuitive interpretation. Number 4. So the family of regular languages is closed under the NOR operation. So NOR or L equals NOR of L1, L2, and the NOR is the set of strings W such that W does not belong to L1 and W does not belong to L2. Okay? So is this regular? Is L regular? Yeah, L is regular. What's the proof?
Complement of L1 and L2
Or regular.
Intersected, yeah. So L is basically, this just nor, it means that it's, sorry, this is the not equal. So the complement of this intersected with the complement of this. So it just means L equals L1 complement intersected with L2 complement. And L1 and L2 are given regular, and regular languages are closed under intersection and complementation. So L1 and L2 are regular, and regular languages are closed under intersection and complementation. Okay. So, this is a good one. Okay. So the last one. Last one. Okay. L equals W has more ones than zeros, such that, or we can do it A's and B's, or let's do it A's and B's, okay? Not ones and zeros. So it just means that more A's than B's. So more ones than zeros. NA of W is greater than NB of W. Okay. Now, this relates to which one? Which question in which part in question 1? The third one?
Yeah.
The second one?
No, the third one is not related because the third one is not related. The third one,
Is the second
you
one?
must have the ordering thing. So you must have A's before B's. But here, NA of W is equal to greater than NB of W, and they can be in any order.
You can give me a second of regular language to make it in the same order.
Okay, so it will not be as direct. It will not be as easy. You may come up with a solution, but it will not be as easy. The most, the closer language will give you an easier solution, right? So when you look at a closer language, you will get a. So I'm not saying that 3 will not give you a solution, but it may be you'll need more steps in order to prove it. But 2 is closer. So L1, which is W such that NA of W equals NB of W is not regular. This can help us prove this, that this is, intuitively. Now, when you look at this, you know that this is not regular. So intuitively, what would you think about this? It should be non-regular. It's about the same. It's like, we cannot basically use finite automata to count the number of A's and the number of B's and make sure that they have a certain relation, whether it's equality or inequality. Intuitively, we expect this to be non-regular. So a proof is just a formalization of our intuition. So we try to come up with a formal or a compelling argument that our intuition is right. So here, how can we prove this? Okay, so I will show you at least one way of doing this. So the relation between this language L and L1, in fact, we can say that L1 union L union L2 is going to equal sigma star. And what's L2 in this case? More B's than A's, right? So you can have either an equal number of A's and B's, or more A's than B's, or more B's than A's. So L2 is W such that NA of W is less than MB of W. So the sum of the, or the union of these is going to give us sigma star. Or you can say that language L is the complement of the union. You can also say that language L equals the complement of L1 union L2. So if a string does not have more A's than B's or more B's than A's, then it has an equal number of A's and B's. So this is one way of, now this will make it easy to prove that, oh sorry, we're trying to prove, we're trying to prove that this is non-regular. So this is to be proven. I mean, there is no single way. I mean, there are multiple ways of doing this. This is to be proven. So I'm going to put the one to be proven here. So I'm going to say L union L2 equals L1, the one that is known to be non-regular. So the union of any two of them, right? The union of the complement of the union of any two is going to give the third one. So now, you know, we can formalize it by saying proof by contradiction. By contradiction. Assume that L is regular. Assume that L is regular. Now, this will imply that L2 is regular. Why? If L is regular, then L2 will necessarily be regular. Why? Exactly, switch the A's and B's. So assume that L is regular, then there exists an NFA that recognizes L by switching or swapping A's and B's in that NFA, we will get an NFA that recognizes what? Recognizes L2, because L2 is just more A's or more B's than A's. That recognizes L2. This implies that L2 is regular. Now, given that L and L2 are regular, we conclude that L1 is regular because regular languages are closed under union and complementation. This leads to L is regular because regular languages are closed under union and complementation. But what's this? We reached this implied that L is regular and L1, not L. This will lead to L1 on the left-hand side. So we assume that this is regular. If this is regular, then it's dual language is regular because we can swap the A's and B's. But regular languages are closed under union and complementation. This gives us that L1 is regular. But this is a contradiction because L1 is known to be non-regular, which is a contradiction. Okay. So there are multiple ways of doing this. Questions? Okay, so the last question, I think number 1 was done in class very much. We did in class something similar to number 1. Go back to the DFAs when we introduced the formal description of DFAs. We did something similar to number 1. So I'm going to do number 2 first. And then if I have time left, I will go quickly through number 1. So question 2. So the idea in these formal description questions is to first draw a DFA and then generalize it. Generalize it using the formal description. So go from the concrete to the abstract using symbols. And here, L is W such that W contains the substring A1, A2 repeated k times, where k is a constant, and k is greater than or equal to 2, and where sigma is a general alphabet A1, A2 through AN. Or sorry, M. Are we using N for anything? So in fact, we're not using N, so I don't know why. Well, you can call it, let's call it M, as doesn't matter. But we're not using N for anything else. Okay, so now let's do it for let's do it for k equals 2. For k equals 2, we know how to construct a DFA for a language that contains a certain substring. So in this case, our DFA will have what? A1, right? Followed by what? A2, how many times? Twice. Then this is an accept state. Then what? Well, here I have anything. So here I can have any symbol. And here I can have any symbol. What else? That's it. So I'm going to call them Q0, Q1, Q2, Q3. For k equals 3, what will this look like? I will have a Q0 with an A1, Q1 with an A2. So how will this differ for k equals 3? Just one more A2. So 3 A2s instead of 1 A2. And then I put the same thing. I have a sigma. I have a sigma. Okay. So now just generalize this. So the whole point here is to see if you can generalize it using the algebraic description of a finite automaton. So we'll have the 5 tuple is going to be Q sigma what? Delta Q0 and F. Now we will generalize it. Q is going to equal what? Q0 in general, Q0, Q1. What will be the last one? What's the relation between this state number and the value of k? It's k plus 1. So the mathematical relation between the last state number and k is k plus 1. So the last one is going to be q k plus 1. Or Q1, Q2, Q3, Q4. Okay, so this is Q. Well, sigma is given. Delta, we'll leave it, we do it at the end because it's the most interesting part. Q0 is Q0. And F is Qk plus 1, the last state. Now delta. delta of q and x, or qi and x, okay. Now given this, now this is the key idea here. How many different deltas should we define, or how many different states do we have here? How many different kinds of states do we have? It's like, there are states that have very much the same behavior, like Q1 and Q2 have the exact same transition, and Q3. So for all of these states, Q1, Q2, and Q3, we have the same transition. Just on an A2, you go to the next. So for these, so for these, just go to the next state. For this, if you get an A1, go to the next state. But if you get any symbol, you can stay. So you have the option of staying in the state or going to the next only if you get an A1. Now here, for this one, what does the transition look like? What? Exactly. If you get anything, stay in there. So this is easy. If you get anything, stay. Here, you have the option of staying. Well, you have this. You stay unless it's an A1. If it's an A1, you have two options. The option of staying or the option of advancing to the next state. And for these, the transition is go to the next state. So we will formalize this. We'll just write what I said in algebraically. So we'll have, if qi, or if I, for I equals 0, we have two transitions. If I equals 0 and x equals a1, we have a certain transition. If I equals 0 and x equals a1, where do we go? Either stay or go to q1. Stay or go to q1. What if I equals 0 and x is not equal to a1? Where do we go? q0. Okay, so this is the first. Now what if I have, now what's the value of I for these states? It ranges from 1 to 3, and 3 is what? K. So it's from 1 to k. So if I is, or 1 is less than or equal to I less than or equal to k, if I is between 1 and k, and x equals what? What's the x that will cause the transition? A2. So the whole point in this question is draw this DFA and try to generalize it algebraically using the formal description or using algebra as opposed to drawing a graph. This is the point. So if it's here and x equals a2, where do we go? We go to the next, which is what? qi plus 1. Now if it's between 1 and k, and x is not equal to a2, where do we go? Well, there is no trap state, so here this is an NFA. Is the question limiting you to an NFA or a DFA? No. Okay, so if you do a DFA, you'll make it harder for yourself.